Dr. Wilczek has been named a MacArthur Fellow, otherwise known as a Genius Award, and he has been elected to the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. Earlier this year, he received the Templeton Prize for boundary-pushing investigations into the fundamental laws of nature that have transformed our understanding of the forces that govern our universe. And the list goes on and on and on, but I'll end with what most people consider the crowning achievement. In 2004, the Nobel Prize in Physics was awarded jointly to Dr. Wilczek, his mentor David J. Gross, and H. David Politzer for the discovery of asymptotic freedom in the theory of the strong interactions. Beyond this seminal finding, Dr. Wilczek has a talent for distilling the high concepts of his work into accessible prose. He has published 5 popular books, the most recent being Fundamentals, 10 Keys to Reality, which was published last year. And I'm going to get I get a copy of the book tonight. The book, by way of its chapter titles, assures us that there is plenty of space. There is plenty of time, which I really like. There are very few ingredients, and there are very few laws, which I like too. And there's plenty of matter and energy, and that's wonderful. Dr. Wilczek's knack for words actually surfaced earlier in his career when he proposed and named 2 types of particles, the axion and the anion. The anion exists only in 2-dimensional systems and is key to understanding how thin planes of material behave in a magnetic field. Dr. Wilczek named the particle after its anything-goes behavior. He named the axion after, and this is so funny, a brand of laundry detergent he remembered seeing in the store as a young child, and the name just stuck. Many in the field of theoretical physics now believe axions hold the key to some of the remaining mysteries of the Standard Model. The search for evidence of their existence is an active area of research, including here on our campus. For example, physics professors Jim Buckley and Cato Murch are part of a large axion detection experiment called ADMX. Their work on this project was part of the Inspiration for Arts and Sciences newly launched Center for Quantum Leaps, which draws upon the expertise of the photonics group in McKelvey Engineering and on collaborations with the School of Medicine. Through the work of the center, advances that began here with Arthur Holly Compton will accelerate, and WashU is set to shape the landscape of quantum research for decades to come. We are incredibly fortunate to have Dr. Wilczek here with us this evening to honor the centenary of Dr. Compton's work, to share his groundbreaking insights, and to highlight the potential of the field here at WashU and beyond the bounds of our campus. And now, please join me in welcoming Dr. Frank Wilczek to discuss photons and vision.
Well, thank you for that lovely introduction. And it's very nice to be back here in St. Louis, or St. Louis. And I have fond memories of my last visit, and I very much enjoyed seeing this beautiful campus today on a perfect day. And I'm, of course, extremely pleased and honored to be associated with the celebration of Compton's great discovery that really cemented the concept of photons in physics as particles. In the introduction, several implications of photons as the inspiration not only for our understanding of electrodynamics, but also for the theory of the strong interaction, and indirectly for axions, and very much in the planning for experiments that might detect axions. But today I wanted to talk about, since this is a public lecture, and also because I've talked a lot about that kind of stuff, I wanted to talk about something a little bit different that I think is another part of the legacy of the Compton effect and the Compton's discovery that is equally profound and very relevant to everyday life. This is the subject of photons and vision. My friend and colleague Sidney Coleman gave a beautiful lecture called Quantum Mechanics in Your Face that you can find on the internet, which I highly recommend, which is a very incisive discussion of why quantum mechanics is so strange and yet not so strange that you can't understand it. This is quantum mechanics not only in your face, but a little bit behind your face, when in the basis of seeing the world as we do. After introducing the profound, almost philosophical connection between photons and vision, I will be honing in on some relatively recent work that uses these ideas, exploits them in new ways, and this is work done with the people listed here: Austin Borchert, Bryson Schenk, Joshua Weeks, and Nate Newman, mainly at the University of Arizona. Or I should say Arizona State University. That's a crucial distinction. So let me just start by making a contrast between our two main senses that give us information about the external world, namely audition and vision. The central idea, if you like, the driving concept of auditory perception, the thing that we actually sense, is sympathetic vibrations of a sounding board. Namely, inside our inner ear is something called the basilar membrane that tapers and also thins as you go down it, and as a result, the resonant frequency of vibrations of this membrane change as you move down it, and the response to different kinds of tones is strongest at different places depending on what the tone is. So if you have the note C, it resonates, middle C, it resonates at a certain place. The octave C would resonate in a different place further down the line, and so forth. It's like an inverse piano where the sounds move the keys. And this makes an analysis of the incoming signal. When we hear a sound, especially if it's a sort of regular sound, a musical sound, we can hear the different notes. Even in chords. Let's do an experiment. I happen to have a piano here. And we'll hit C, E, G, B flat. That's the C7th chord. If I play the chord, you really can hear each note within it. They don't lose their identity. That's quite different from color. However, if you think about it, that's kind of a paradox, because at the basic physical level, they're both vibrations, both periodic disturbances. One is vibrations of pressure in air, the other is vibrations in something a little less familiar, maybe, although students of physics become very familiar with it as undergraduates. That is, according to modern physics, visible light is a special case of electromagnetic radiation. That is, it's a self-perpetuating, propagating excitation of electric and magnetic fields. This is something that emerged as maybe the pinnacle of 19th century physics in the work of people like Faraday and Maxwell. And visible light, which was mainly all that was known at the time, corresponds to only one octave within the spectrum, within the possible frequencies of light, of electromagnetic radiation. So a factor of 2 is an octave in sound. And all these other things were predictions of Maxwell's equations, and now, of course, are things that are all around us and used in technology in everyday life. But for this lecture, I want to concentrate on visible light and this contrast between things that at some level are otherwise very similar. For instance, you can analyze light into its component pure tones. That's what a prism does. That's what you see, that's what water drops do when you see rainbows projected on the sky. But that's not what our eyes do. We don't see it that way. When we respond to a beam that contains a mixture of colors, we don't have and experience anything like a chord of music. We see just a different color. In fact, sometimes we see the same color as a pure spectrum, as a pure tone. The pure tone can also look like something that's a combination. We'll come back to that very much later in the lecture. So, why? It's because of quantum mechanics. It's because of the phenomena that Compton really solidified in our understanding. Quantum mechanics changes everything. You can't understand how humans perceive light fundamentally without taking the quantum nature of light into account from the beginning. In fact, there are 2 key aspects of qualitative aspects of quantum theory that really determine the nature of human vision. One is that it's based on all or none response, and that's an aspect of photons. The electromagnetic disturbances transmit their energy in lumps, and they can't be broken up into smaller units. They can't be, you can't have a continuous response to them. And the response is probabilistic. So it either happens or doesn't happen. So a photon may or may not get absorbed, may or may not excite a certain process. If it happens, it's total absorption. If it doesn't happen, but it doesn't necessarily happen. So more concretely, human color vision is based on 3 different kinds of proteins called opsins that surround retinol, which is the thing that absorbs light. They surround the retinol distorts the opsin, and the change in the shape of the opsin triggers electrical responses that are the signals that are used inside our nervous system to transmit and interpret information. So these are what the opsins look like. Biologists will recognize these are G proteins. They're membrane proteins that go up and down 7 times. They're part of a large and ancient family of proteins. And there are 3 main types in the human color vision system, which are sometimes called L, M, and N, but colloquially, it's easier to remember that they're blue, green, and red for where the responses kind of are most sensitive. And you'll notice here that the green, it's important, the thing I want to further emphasize in this slide is that the green and the red differ only in a few places. So in evolution, they had a common ancestor, and then just a few mutations differentiate the modern red receptor from the modern green receptor. And we'll see that leads to different responses, but it also leads to the possibility of color blindness when these mutations are not all in the right places. So when they sort of revert to the prototype. So again, the shape changes are all or none in response to a given photon. It either happens or it doesn't happen. If it happens, it's always exactly the same. If it doesn't happen, it doesn't happen. But it happens with a probability that depends on the frequency of the light. So for the photon receptors, instead of a resonant response at a particular frequency, you get a probability curve, also called the sensitivity curve or the response curve of the different kinds of receptors. And they look roughly like this. The blue is peaked towards the blue. The red and green are not very different, as I advertised, and they are peaked more towards the long wavelength part of the spectrum. Those are the kinds of receptors that give us our color vision. There's also another kind of, those are so-called cone cells. There's also the rod cells, which are more abundant, but are in region, give us night vision and really come into play when the light level, illumination levels are low. And at night, you may notice that the world looks less colorful. It just is sort of different shades of gray. This is a picture of our hero, James Clerk Maxwell, as a young man. Maxwell, in addition to his fundamental work on electromagnetism, and the electromagnetic theory of light, spent at least as much time during his career working on the perception of light. And this picture, in a way, demonstrates that. Back in the early to mid-18th century, when this picture was taken, taking pictures was a serious business. It required sitting still for a long time. It was rarely done, and people prepared, you know, he's obviously dressed to look his best, combed his hair, and posed. Well, what is this thing? Why in the world does he have this toy in his hand? Well, this was a toy that was very important to Maxwell. In fact, it was the tool that he used to elucidate the nature of human color perception. He made a crucial discovery using this kind of toy, which he called a color top. And this is the idea. On the top, you have 2 bands, 2 angular bands, and you can put dyed papers on the 2 bands of different colors, and then you can twirl them around and ask the subject whether they can perceive a difference in the color. And Maxwell bought many different kinds of dyed papers of different kinds, and did painstaking experiments to show that using just 3 different colors on the inner band, he could match any color in the outer band. So the perception of any color could be matched by a mixture of just 3 colors. You twirl them around and they look the same, even though physically the light that's arising is quite different. This is the basis of large parts of modern display technology. Okay? Since you can get away with 3 colors, that's the way to go to make things efficient and cost effective. And so this is an iconic figure of the mixing of different colors of beams. And you'll notice, for instance, something I mentioned earlier, that a pure color, a color of the rainbow, yellow here, is reproduced by mixing red and green. So the yellow in your computer screen is typically actually a mixture of red and green. It's not spectral yellow. That's quite different, but it looks like spectral yellow. Now, you may remember back in kindergarten when you played with crayons, mixing red and green certainly doesn't give you yellow, right? But the point is that adding colored pigments is a very different thing from adding colored beams. Pigments work by reflecting light and subtracting some of the color by absorption, whereas beams are direct. And part of the genius of Maxwell with these colored tops was to be able to produce the effect of beams, which weren't easily available at the time, by relying on the eye to integrate different colors that you got by pigments. Okay, so it's not drawing one crayon on top of the other, but putting them side by side and twirling. And later on, the Impressionist artists also used this kind of technique in a different way to get mixtures of colors by putting them next to each other, but not on top of each other. So then you can get the beam colors instead of the pigment colors. So that's how the basic quantum nature of light plays into our perception of light. Okay? And you have, instead of a resolution into pure tones, you have 3 kinds of receptors that have response curves, and it's messier. So can we reinstate some of the information that our perception fuzzes up? And can we understand this quantitatively and use our understanding to address questions like color blindness as well as enhancing of sensory perception? That's going to be my theme for the rest of this discussion. So, as Maxwell showed, different physical beams can look the same. Thus, those beams are called metamers. This phenomenon is called metamerism. You can have physically distinct patterns of electromagnetic radiation that look the same. There's a useful and interesting way to get a grip on this using the concept of invisible beams. So I'm going to use a little bit of algebra now. I hope this is not too horrifying, but if not, I'll summarize the message at the end. So suppose we have several illumination sources, and we have several different kinds of detectors. So this might be the different cells in your eyes, but they also might be in a robot or some device that you want to think about. Then we have the responses to those illumination sources. So the illuminations have different wavelengths in them, and they're a spectrum of different wavelengths with different intensities, and the detectors respond proportional to those intensities. That's what's being said here. And then the total response of detector alpha to source K is you sum over or integrate over all the wavelengths. Now, suppose you have a combination of intensities that is 0, as seen by all these detectors. That's an invisible beam. It doesn't have to be physically 0 at every wavelength, just the total is 0. And this is a mathematical equation you can analyze. It defines a space of possible illuminations that are invisible. We call this the space of invisible beams. Now, it's very nice to have a linear space because there's a subject called linear algebra, which allows you to say quite a lot of intelligent things when you have this kind of setup. So we have alpha equations, where alpha is the number of detectors, and K unknowns, where K is the number of illumination sources. And according to the general principles of linear algebra, we should expect that if the number of unknowns is equal to the number of equations, there's a unique solution. And since you see nothing, the unique solution is nothing. But if the number of unknowns exceeds the number of equations, we can have solutions that, we can have ambiguities in the solution, and we have more solutions and a whole space of solutions. So if you don't know the linear algebra, it's very intuitive to say that if you don't have enough measurements to match the number of things you're trying to determine, you're going to be left with an ambiguity in your fitting the data. But this is a precise version of that is appropriate in this case, where everything is linear and straightforward. So, for instance, if we have 4 illumination sources and 3 detectors, like the 3 cone types, then all the invisible beams will be a one-dimensional space. They'll all be multiples of one particular combination of beams that we can compute by solving the equations I showed you on the last slide. But there's an important subtlety, which is that linear algebra can bring in negative intensities, okay, but physics can't. And in fact, you might be disturbed by the idea that there are invisible beams, but they're just in art. They're not something you can produce physically, for better or worse. They are, because they must involve some negative intensities, so that the sum of the positive responses can add up to 0. Multiplied by those intensities can add up to 0. So we can't make a real invisible beam, but we're very accustomed to working with negative numbers, negative temperatures, negative things. It can be very useful. Even, we'll see, negative probabilities. So what we can do is, well, what is the negative number? A negative number is kind of like an IOU. You have to compensate with a positive number to get something positive. So we start with a non-zero illumination, and then add a little bit of this invisible thing, which has some negative illumination. But if we start positive and add a little bit of negative, it's positive. So that is something physical. So what you can do is start with a physical illumination, add a little bit of this virtual invisible beam and get physical invisible beams. In fact, all of them you get this way by analyzing in terms of adding in some of the invisible beam. So in that way, we can predict how, in a very precise way, how you can change the nature of the beam without changing the perceived color. Okay, this tells us how to do it exactly and precisely, quantitatively, if we have control of the illumination sources of their intensity. And I'll just add this as an aside for my colleagues. There are very similar tricks for other really neat problems, like you can have different objects that have the same inertia tensor and therefore behave all the same way under rotations. And to quantify those, you can bring in negative masses. And in quantum mechanics, you can have things that look the same to a suite of observations, and those define equivalent density matrices for those observations. The space of things is that if you want to quantify what those are, you bring in negative probabilities that you can add to a given central example and sweep out all the possible solutions. Okay, so that's the end of the kind of more formal discussion. Now I'd like to talk about an application to very practical and interesting class of problems. There are many anomalies in color vision that people have due to different forms of those underlying proteins that respond differently to light, have different response curves, different probabilities of absorbing photons of different wavelength. And here are 10 of them. So normal vision, as we said, is trichromatic. There are red, green, and, well, normal vision means majority vision, to be politically correct. But I'll use the word normal. But there are differently enabled people of different kinds. There's the proto-anomaly, which is a mutation of the red receptor that sort of shoves it, roughly speaking, shoves its response so that it's more like the green receptor, shoves it a little bit towards shorter wavelengths. And that gives people that gives the still trichromatic vision, just different. So they're differently enabled. And in fact, as we'll see, people with this proto-anomaly can perceive differences in color that people with normal trichromatic vision won't perceive. And we can be very precise about that. And the most common color blindness is this Deuter anomaly. That's a mutation in the green receptor, which kind of makes it more like the red receptor, shoves it over a little bit in wavelength to make it more like the red receptor. But then there are a whole bunch of other ones too. This gives you a more minute sense of what the different possibilities are. So there's normal, or more concrete in terms of response curves. So normal, these are still artist's impressions of the response curves, but correct in spirit. There's normal trichromacy, like that. And then there's deuteranopia, where the green receptor is just missing. Deuteranomaly, where the green is shifted towards the red. And then, very interesting, you might inherit from your mother one gene, and from your father another one. So you might have one copy of the mutated gene, but also a copy of the normal gene. In that case, you are a tetrachromat. You have 4 responses. In fact, there are 2 different kinds of, well, theoretically, there are 2 different kinds of common tetrachromacy, but the literature on this is very sparse, surprisingly. That's a situation we want to correct. And you can even imagine pentachromacy, where the common mutations of the green and red are both present, together with the normal versions, and then you have 5 different kinds of color receptors. That sounds impressive, but the bad news is that they're all very similar, so that the distinctions, that the extra power is subtle. Okay, this is meant to give some idea of what the different experiences of these look like. I found this on the web, and I think it's actually mislabeled, but I won't go into, in view of the time, I won't belabor it. But this protanopia should be absence of the blue receptor, but clearly this is missing both blue and red, and so yeah, the labels are wrong, but it shows that if what you're missing if you have different kinds of color anomalies. On the other hand, there are creatures in the natural world that have many receptors, many color receptors, and a world of color that is not something we share. The most extraordinary one is something called a mantis shrimp, and mantis shrimps are a very successful species, a very successful genus, I guess, that has several different species, and are found very commonly in semi-tropical waters and tropical waters near the shore. I'm afraid that they're also eaten a lot, but they have, depending on the species, from 12 to 15 or even 16 different kinds of color receptors that expand into the ultraviolet and also into the infrared quite a bit. So that's inspiring. Can we expand our experience so that we see the world like a mantis shrimp? We'll see. Okay, so let's first discuss quantifying and diagnosing these color vision diversity. Here is another way of seeing how the different variations affect the perception. And these are more realistic response curves, and you see that the differences between the typical trichromat and first of all, that the difference between the red and green receptors is actually not all that much. And secondly, that the deuteranomaly changes it in this particular way and the protoanomaly like this way. So then the difference becomes even less, but it's a subtle effect. This is a beautiful way, I think, a very instructive way of plotting sensitivity that shows in a real sense that we're all very colorblind. So the blue response curve, so here the sum of the responses is normalized to 1, so we divide by the total and plot the ratios here. And when the ratio is fixed, as a function of wavelength, then really all you can see is how bright it is, because the different wavelengths all look the same as far as ratios are concerned. So there's only one degree of freedom. Your vision is one-dimensional. In a sense, it's just black and white in that region of colors, of spectral colors. So here, out in the blue region, our normal vision is one-dimensional. Here it's two-dimensional. It's only in this sweet spot where it's really three-dimensional, where all the ratios are changing, then it becomes 2 and 1 again. And in the other, in these most common forms of color blindness, you see the region of three-dimensional vision is even smaller. But even in the normal trichromatic case, true trichromacy is only in a very limited range of wavelengths. So it's a disgraceful situation that we should try to do something about. Okay, so we can calculate for given illuminations, if we want to make a test for and diagnose these differences, we can have illuminations that we choose, and we can go ahead and calculate based on these response functions what the invisible directions are and they're different for the different kinds of anomalies. So to test whether someone has a given anomaly, we can add in things that should be invisible if you have normal vision, but will show up as differences if you have one or the other anomalies, and so forth. So you can test what different people see as different. And it's actually a marvelous thing that this shows that it's really true that people who have so-called red-green color blindness, it's not a defect, it's a different sensitivity, because those people can distinguish colors that people with normal trichromatic vision can't. It's just that it's a normal trichromatic world and it's built around the sensitivities of the normal trichromats. Okay, so I hope you get the logic here. We can figure out what looks invisible to different kinds of people. If we have 4 illuminations, we can see how to tune things so that things look the same to people with a given kind of color vision, but will look different to the other ones. And that enables us very quickly and accurately to diagnose all these things. And I'm really looking forward, actually, and this is tested and works. I'm really looking forward to finding tetrachromats, showing that there are 2 versions, and maybe finding a pentachromat somewhere. And this would enable us to really document that ability. Yeah, so here's what our little prototype devices look like. You either see a difference or you don't, and we predict and you can do several different anomalies at once by varying in the invisible metamer direction to see if the person sees something changing or not. This contrasts with the classic way of diagnosing these things, the so-called Ishihara plate, where someone is shown these, you've probably all seen these, where someone is shown things like this and asked if they can they see the number in the middle, and you have to look at many plates. It's a slow process, and yeah, we do better, I think, much better. Okay. A very interesting possibility in the same class of ideas is this. Suppose we want to make the world look to someone who's differently enabled vision to see the world the way someone with normal, majority vision shows, or vice versa. So we want to have two different responses, response matrices, see the same thing. Okay. So to do that, we have to map, well, we have to have this condition, okay? So it's the responder with the response matrix N will respond to the tilde beams here in the same way that M responds to the beams. What is that condition? Well, those of you who know some linear algebra will know how to solve this equation. It tells you that you should take as your B tilde just inverse matrix of N times M. So this tells you if you want to reproduce the sensation of a given mixture of colors, and remember you can get them all from 3, for someone with different perceptions, there's a calculable matrix transformation that does it, and that's it. Okay. There are complications because this N inverse M may have negative entries, or the colors might, if you have a display, they might get too big to be displayed, but we have, well, you can fudge those, and I won't go into it. Here is a demonstration of what the mapping actually looks like. It's still in the works, so but this is already shows the spirit of the thing. So here you have one of the Ishihara test plates, and normal tetrachromats are supposed to see a 73 here, obviously. If you do the mapping to get the sensation that someone with the Deuter anomaly should get from this, and you're, of course, a normal trichromat, this is the mapping, that this shows you what the Deuter anomaly person sees. And sure enough, there's no sign of a 73 in there that I can see. But now, if you apply the mapping that is supposed to make this look like this, you see it does a pretty good job, and there's the 73 sticks right out. If you apply that same mapping to this, it looks quite bizarre, but that's the same treatment. So this looks like this, which is supposed to look like that, if you know what I mean. Okay. And similarly, this is for the protoanomalous, the other kind of common color blindness. And you see, we need to do some work to get the brightnesses to match better, but that's a normalization that hasn't been properly fixed. It will be. This procedure, we can check against the Ishihara tests, and it's been extremely effective in enabling people who have anomalous color vision to pass for normal trichromats on these processed images. Okay, let me conclude with another direction, which I find really inspiring and kind of open-ended now. This is initially an idea that was initially developed in order to enable a student who is kind of inspiring, who had achromatopia, which means no cones at all. So only rods, and therefore sees the world in black and white. But not only that, because the rods are easily saturated, they're normally turned off in daylight, but come into play in low illuminations. People with this condition get totally blind in bright vision, in bright environments. This is beautifully, it's a rare condition in the general population, but it has a big hereditary component, and there are populations where it's endemic, where it's very common. And this is described in Oliver Sacks' Island of the Colorblind, where he visited an island where many people had this problem. And so that's very interesting to read. Anyway, Sarita was given glasses, something like this. That first of all took out a lot of the light, and the remaining light is red, so its long wavelength doesn't tend to saturate so much. But then by moving her, so that's good, but also by moving her head up and down a little bit in these gradient glasses, the spectral character of what she sees is different. So, and that enables her to get a two-dimensional color view of the world, even though even though it's just the cones responding, because the glass has modulated the input beams. And this has been a big success story, and we're hoping to export this to the island of the colorblind. So the next step is we're going to give Sarita superpowers of vision that even exceed normal people's perception of the physical world. By moving her head up and down, she'll get different views of the physical world that bring out what's normally encoded as color. And this is now a scientific endeavor. We know what we're doing, and we know how the dyes work, so we can tailor these gradients. And we could do the same thing for color, for less severe color anomalies. So to have people, if they want to, if they're deuteranomalous, for instance, be able to accurately get an idea of what normal trichromats are experiencing just by moving their heads up and down a little bit. Or vice versa. Or we can add extra dimensions of color perception just for the fun of it. You can start to be like mantis shrimps, but with better analysis abilities, hopefully, than the mantis shrimps. Also, we can go into other parts of the spectrum, parts that are not necessarily accessed in ordinary vision. We can bring in ultraviolet vision in particular by having fluorescent molecules that twinkle and have different densities and thereby sense the ultraviolet without being too disruptive of normal vision. And we can do polarization too. It's all the question of what goes into the dyes that go into the lenses, and that we can control. So here are some of the things. And I've walked around Concord in Tempe, Arizona with these things, and it's really cool to experience the world differently, the visual world differently as you move your head around. It's really eye-opening, so to speak. So I'd like to close with this extract from William Blake, which I found extremely inspiring in this investigation and in life generally. If the doors of perception were cleansed, everything would appear to man as it is, infinite. For man has closed himself up till he sees all things through narrow chinks of his cavern. So we're opening the doors of perception. Thank you.
Okay, so thank you very much, Frank, for that amazing perception door opening experience. We have a little bit of time for a few questions. So if you'd like to ask a question, would you mind raising your hand, and we will have an assistant bring you a microphone so you can ask a question. Would anybody like to ask a question? Okay, we have a question there.
Is there a possibility in the future you could digitally have a digital pair of glasses that could alter
Sure.
wavelengths and...
Well, it's possible, yes. That's more high-tech than the things we're doing now, but yes, it's certainly possible, and maybe an interesting direction to go. But it raises, well, it's a second-generation project, I would say, because you have to have materials that respond to signals, presumably electrical signals, and then you have to bring in the signals. But it's certainly possible in principle. You know. And yes.
Thank you very much for the beautiful talk. I just have a more maybe philosophical questions. Back in ancient mythology, you always hear stories about cloaks. Now, what would it take to take away all the visual perception by a physical cloak?
By a cloak?
Yes. Is it physically possible?
To make yourself invisible, to make things invisible. No. Basically. Although I should say there's been quite a bit of activity in the recent physics literature, which maybe you're alluding to, about invisibility cloaks. But that has to be taken with a huge mountain of salt, because these cloaks typically are just ways of diverting light or electromagnetic radiation in certain frequency bands so that it moves around the material, but only at certain angles, only at certain frequencies, so it's not general. Photons are very good at propagating and scattering off physical objects, so I don't think it's a practical proposition to build any kind of invisibility cloak that would be versatile and well. Let me give another example. Actually, stealth technology for airplanes is highly developed to enable them to evade radar detection. And it can be effective, but it's effective for radar detection, and it's only partial. You get less of a signal, and so and to do that, you have to go to great lengths in terms of materials and shapes, and so it's and a lot of money has been put into that, so it's awfully tough. And I think there are even quite difficulties of principle, though I'd have to think about that a bit. The Invisible Man's a great story, though. H.G. Wells, yeah.
So there's been a lot of recent developments in TVs and displays using quantum dot technology
Yes.
to like select specific wavelengths. Are you using similar things for the color glasses, or are you looking to use that or
At
not?
present, it's very much lower tech. We're just using dyes that are available, but because they're, that are cheaper. But yeah, if there turns out to be demand for this kind of thing, and people are interested in a premium product, then yes, that's certainly a possible way to go.
So, using these glasses, will we see more colors, or will we just see more differentiation within the colors we see?
No, we're still limited to the 3 cones. I mean, well, there are, or maybe 4 if you're a tetrachromat, but so we're not changing the C's, so that we're not changing the response curves, but we're multiplying the C's we have by different factors, if you like, as you move your head. And so, in effect, we're synthesizing additional receptors, but we're not actually. So you still see the same kinds of colors, you just see a different mixture as you interact with the world and move your head around. It's really quite striking psychologically, though. I can attest. All right. And of course, if you do this fluorescence, then you really will directly experience ultraviolet, for instance. So you can do tricks like that to direct. So it wouldn't be a color; it would be a kind of shimmering. But no, it doesn't make sense to say, well, what does ultraviolet really look like? It doesn't look like anything to humans. We have to make it to something.
Thanks for a great talk. It's kind of related to what you're saying just now, actually. Not sure if it makes sense, because I was thinking, say if like the mantis shrimp can see like infrared, they might see a light and they think that it's hot. It looks hot to them, potentially. I'm just wondering if like when people can see extra, say different colors, shades of colors, or how would they like behave differently? Would they like, how do they change psychologically? If that makes sense.
Well, I'm not sure if this really addresses your question, but in fact, we do sense infrared, basically in the form of heat. We feel hot in response to infrared radiation. You feel it. It raises, it's a sensation of heat. But we don't. It's qualitatively very different from vision. It has no, or very, very little spatial resolution, for instance, and is not processed in the same way. I'm not sure, so you can imagine actually things, you can imagine translating different color perceptions not into different kinds of sensations. For instance, you could change them into tapping on, tapping at different frequencies if you're seeing, if there's a very bright source somewhere. You can certainly do that kind of hardware image processing. And maybe there are good ideas in that direction, but it's not a direction that we've explored very much. We're trying to make enhancements of vision that are still recognizably vision and keep the very, very, very good features of vision that our brains do a tremendous analysis of the visual input that comes into our retinas. So all kinds of information processing and feature detection, and we have very good spatial resolution. So very poor time resolution. That was the whole point. In music you have very good time resolution, but very poor spatial resolution. Vision is just the opposite. But what we're trying to rescue sort of some more of the time resolution by keeping the spatial resolution.
Hello, thank you for the nice talk. I have a question about the glass. In order to change the perspective of the colorblind person, from my understanding, we can use some glasses, but the response matrix of that person won't change, right?
That's right.
Yeah, I wonder how can this kind of...
Well, it does in a sense. Let me repeat. So there were these response functions C as a function of lambda. So that's the response. Now, so you multiply the C's times the intensities to get the actual response. If you have glasses that themselves have a response function, so then C, in effect, gets multiplied. C of lambda gets multiplied by the response function of the glass.
Yeah,
so instead of just your original C, you have C times R, the response. And so in effect, you're synthesizing additional kinds of receptors because it's different response functions.
Yeah. So my question is, can I understand this as we modulate the impulse that for that patient instead of let them use their eyes to observe the world directly?
I'm sorry, I guess I missed.
That is the modulation of the
modulation,
impulse.
yes.
Yeah.
So, I mean, to be very concrete about it, although actually we haven't done this kind of experiment, it would be very interesting a challenge would be to have glasses that someone with a Deuter anomaly could put on that then by moving their head they could pass the Ishihara tests.
Thank you.
I think that should be possible, and that would be a very concrete demonstration of the general concept. Yeah.
Okay, so thank you all for coming, and thank you all for your questions, and most of all, thanks to Frank Wilczek.
Okay,